Hello. Okay. So let me first discuss the insertions. Um, so recall path integral in non-relativistic quantum mechanics. What we had there is the path integral dxi to f e to the power I by h bar s I f x, and there's a bunch of insertions that is equal to the matrix element between f and I of the time ordered product of those operator versions of the insertions. So these insertions are dynamical variables involving x, x dot, and so on. And these are corresponding operators in Schrodinger theory. Okay, so this is the statement. This defines all possible computations that we could do in this in that theory. So in the context of the relativistic particle, we have not developed this this language. Language not developed. I mean, in the course only. It's known. However, we can consider this side and consider that to be the full set of computations that we could do using in the worldline theory. Now, question is that how are these insertions interpreted? It is important in our goal to show the equivalence here, as we will see as we go along. It is important to, in order to show this equivalence, it is important to understand this this physical what is the interpretation of these insertions are. So how should the insertions be interpreted? That is the question, and the answer is that insertions are related to presence of other backgrounds. These are related to presence of other backgrounds, background fields, and the complete analysis of this statement is beyond the scope of this lecture. So complete analysis is beyond scope of these lectures, However, let me pick a familiar example to make the point so that you have a feel of what I'm talking about. So a familiar example is say scalar QED. A scalar QED is a theory that describes propagation of a scalar particle which has both mass and a charge in a background electromagnetic field. So your diagram, relevant diagram will be this, where the particle, so you have a background electromagnetic field, there's an electromagnetic field background, and the particle has a charge so that it couples to that electromagnetic field. So it has, there are two parameters, mass and charge. Now, so the question is, what is the worldline path integral? Of course, the worldline path integral, the initial geometrical, all the geometrical remarks and features are all the same here, except that the worldline action must be different, because it must, the result must depend on the background A field. So this, in presence of a background A field, must be given by the same expression, except that this is now Z lambda MA. So my notation indicates that this A is a classical background which is not path integrated. So this is a classical background not path integrated. And so the question therefore is, what is this action? This is the question that we are going to answer. So recall our previous approach. The same approach should, we should adapt to the same approach here. Recall previous approach. Which means that this action Z lambda A must reproduce the same classical equation of motion of a charged particle in presence of mu, must reproduce, that was the approach we took earlier in the context of a free particle, must reproduce same, must reproduce known classical equation of motion of a charged particle in presence of mu. So how does the action look like if you have to reproduce the same equation of motion? So we must have worldline Z lambda A to be equal to worldline Z lambda plus and S interaction Z lambda A, because when A is 0, we must recover the previous action. Okay, so this is the interaction, this represents the interaction. How do we find the interaction? So to find the interaction, let's consider space-time action. Classic, let's consider the space-time action. What is the space-time action? The space-time action has all these fields, right? Z, lambda, and A, all at equal footing. They are all fields. The space-time action will have a part which describes the dynamics of the Maxwell fields, so that that is the action corresponding to A, such that the equation of motion coming from SA are Maxwell's equations, and then the action for the particle, which is of course supported only over the line. This action is supported over the four-dimensional space-time, but this action is supported only along the world line. So that is therefore given by ZL, Z lambda plus S interaction Z lambda A. Okay. So when you write this action, you have a four-dimensional integral, and the integrand is a Lagrangian density. And in this case, as we have seen both in these two cases, we have a worldline integral ds, and we are trying to figure out what the integrand should be. We know the integrand here, but we are trying to figure out what this should be, right? So as I just said, that from here, you should be able to calculate equation of motion, and this equation of motion is nothing but Maxwell's equations with source say J mu. There's a current, and we know that Maxwell's equations in presence of a source current J mu, the equations are linear in J mu. We also know that this equation of motion is given by del S, del A mu, del S of the total action is equal to 0, right? So on one hand, we know that the equation of motion must be linear in J mu. On the other hand, we know that the equation of motion is given by the first order derivative of this action with respect to A. So then the interaction must be A mu times J mu, because when you take a first order derivative with respect to A, it gives you J. So this observation tells us that S interaction Z lambda A must be given by A mu x, J mu x. A mu is a four-dimensional field. J mu also is a four-dimensional field in general, but we now specialize to a particular situation where a charged particle is moving, a charged scalar particle is moving, and you have to just find the J mu corresponding to that. And we know how to do that. I'm not sure if you are familiar with this, but you can learn now. So what we have here, we have a world line. There's a four-dimensional space-time X, but then in that where A mu of X lives and as a field, but the source for A mu is only supported along the world line. So that is your Z mu of S, the trajectory. And the reason it is a source for the electromagnetic field is that it has a charge E, and but charge E is not enough. It must be moving in order to produce, the full current, and the current is therefore given by E times integral ds. So the current is that E times the velocity, so d Z mu ds, and but you are supposed to write a four-dimensional field, right? This is a you are supposed to, so you know that current is supported only over this, in which case the current is basically E times dz ds. So it is E times dz ds. That is the current at this point. And but you want to write it as a you want to write it as a four-dimensional field. How would you do that? What you do is that you integrate the current along the trajectory, and then the value of x must be same as z mu of s. This is how you describe it. Now you can check that. So it is first of all, it's a four-dimensional field because it's a four-dimensional field. X appears here, and then the S-dependent fields are all integrated over S, and so if you choose any value of x, let's see how you find. So this is my claim is this is J mu. So how you calculate, how you find given any value of x, how you find J mu x. So let us see if we have written it right. So you pick any point here, say x, and calculate it. Okay. So what is the value of the current here? The current value of the current must be non-zero only over points which lie on this point, on this trajectory. So if you pick a point here, it should be 0, and that is true because there is no value of s in this entire integral when x is going to be same as any point on the trajectory if you choose x to be here. Okay. But if you choose x to be anywhere on this trajectory, then there is a corresponding value of s for which x will be same as z mu s, and you will get the result. And that is why, so, and this has to work for any x whenever it lies on the trajectory. And that's why we have to integrate over s to provide all possible legitimate values of x to be lying on the trajectory. Which is what the reason for the integral of ds is. So therefore, basically the result is E times integral ds. Now you impose this delta function on a mu also, and what you get is a mu zs times z dot mu. Okay, that is the interaction Lagrangian. Now notice that this this combination here is invariant under S reparametrization without any involvement of lambda. Earlier we had two derivatives. Here, and there is only one integration, right? So ds. So under S reparametrization, these two effects will not be cancelling. This will have a Jacobian factor, and this will have inverse Jacobian factors. So they will not cancel, which is why we needed a lambda, which will also transform under S reparametrization such that the entire thing is invariant. But you don't need lambda if you have only one derivative, and that's what is happening here. So this is invariant. Let me. When you do S reparametrization, it is not only this portion that you should look at. You should look at this portion as well. How does it transform under S reparametrization? Let's have a more serious look at it. So under S going to S prime, you know that Z mu of S goes to Z prime mu of S prime such that it is same as Z mu of S, because Z mu is a scalar field on the one-dimensional world line. So basically the support of the delta function does not change, because the support of the delta function is when x is numerically same as this. It is x mu is numerically same as Z mu of S. Under reparametrization, the functional form of Z changes and becomes Z prime of the new parameter S prime, but keeping the same value for the numerical value for z. So z prime s prime is same as z is. So this numerically this does not change, and therefore the support does not change. So it is invariant under S reparameterization. So so that this means this in this expression is invariant under S reparameterization without having to use lambda. Okay, so therefore the conclusion, let me try to write it here. So the conclusion is that matrix element fi in presence of A is given by integral dz d lambda over v e to the power I by h bar s worldline z lambda, one that we had earlier, then I e over h bar integral ds a mu z is z dot mu. Okay, and this can be written if you expand this part of the exponential. If you expand this part of the exponential, then it can be written as integral dz d lambda over v e to the I by h bar is worldline z lambda times if you expand that exponential in powers, then this is 1 plus I e over h bar integral ds a mu z times z dot and so on. And so now if you take this product, the first term is just this standard phase, path integral phase for the free particle, and the next term is that is appearing in this free particle Lagrangian, in this free particle path integral as an insertion. So this is an insertion, right? It's an integrated insertion. Similarly, second term will have two factors of a mu, right? So those are insertions, and they will look like, if you wanted to draw Feynman diagrams, then it would look like this. This is the first term. Then up to a factor, you will have the same propagator, but an insertion here somewhere, which is basically, which will be integrated. This insertion will be integrated, but that connected to that insertion is some background a mu field that is coming in. That depends on the location, that the factor, the strength of that insertion is given by a mu at that point, right? And then there is another term, there will be another term which will be having two insertions, and so on. So this is how the effect of background looks like, because when you are expanding, so there is an expansion in powers of e, because each factor here comes with a factor of e here. In the second term, next term, there will be a factor of e square. So if e is small, it's like a perturbation expansion in e, and what you are getting is that entire so this entire result is like a 2-point function, but it is not the usual field theory usual free particle 2-point function, but it is involving it is taking into account all possible reactions with the background. So what it shows is that the insertions that when you started out with the path integral for free particle, you would naturally ask this question, just from what we learned in the non-relativistic case. Naturally ask these questions: what about the insertions? Those are possible computations. What we see here in this argument is that these insertions correspond to because here, see, earlier we did not have this feature, because insertions here have some space-time properties, because these are insertions. Earlier we had insertions of x, x dot, and so on, and now we are calling it z. This z has an index mu, so insertions will have tensorial properties, and therefore the couplings to those insertions, the factors, because the entire thing is Lorentz invariant, the interaction is Lorentz invariant, so this is Lorentz invariant. Whatever insertion you put in, if you want to calculate it in a Lorentz invariant manner, you must be multiplying z mu dot or whatever higher derivatives of z, z mu with the corresponding tensorial object here, which can depend on z in general. So these are the this is like a general term which has a first order derivative of z. So you allow a z dependence in the coefficient. So therefore the coefficient of that insertion becomes a tensorial field in the theory. In your calculation, you are automatically considering, while considering insertions, you are automatically bringing in some fields with certain Lorentz properties. And what I just showed is that depending on what insertion you choose, if it is x dot, then the field that it is bringing in is basically a background electromagnetic field, and it shows that can happen only when the particle that is moving has a charge. Then only it can couple. I mean, you can always, insert something like this in any worldline theory, but in order to do a physical interpretation of that, you interpret that particle to have a charge. Otherwise, why would it couple to a vector field like this? So this understanding helps us in interpreting whatever insertions we could have. This is helping us figuring out what theory we are trying to describe. So if you do not want to describe a theory where there are non-trivial background fields with which the particle is coupling. So for each, if you have to have other type of insertions, which is qualitatively different, not higher powers of the same, but other type of insertion. Let's take z dot square. It is not z dot square. It will have, next term will be the entire term to the power 2. That's different from z dot square. When you have the entire term to the power 2, then there will be, it is right that there will be two factors of z dot, but each one will be coupled to a separate a mu. That's different from having z dot square and having z dot square and having that multiplied with a second rank tensor. So that's a different object, and so you can take all possible insertions and classify them and see what they mean. So that new field, if you take z dot mu, z dot nu, and couple it, multiply with a coefficient, say g mu nu or h mu nu of z, then this h mu nu of z is a new background field with which the particle is coupling, and you have to figure out how to interpret the coupling, corresponding coupling factors, and so on. There are ways to do that. That is precisely why I'm saying that I'm not uh, uh, we will not do a complete analysis of this problem, but this can be done. All I wanted to motivate is that this complete analysis is beyond the scope. All I wanted to motivate is that those kind of insertions are related to backgrounds. If you do not want to consider backgrounds, you forget about those calculations, those computations. Okay, so this was this slide.